So now we'll run through the calculation for the importance score, and we'll see how to go about that. And you'll see it's very mechanized, so you can use this, and you can do this for basically any web graph that you're given and follow kind of the same procedure, and it'll work out. So here's our web graph over here again. We've noted the links accordingly with their values, for instance, W over 2, Z over 3, and so on, the spreading of the importance scores. And we'll tabulate our equations that we just got in the last video over here, because we'll need them to solve for the importance scores, because these equations give the relationship amongst the different importance scores. And so one thing you'll notice right here is that we have 4 equations. Right, so we have 4 equations, 1 per node. We went W, then we went to X, then we went to Y, and then we went to Z. And we got 1 equation each, and we have 4 unknowns, which are the importance scores W, X, Y, and Z, as we said before. And so you'll probably remember from an algebra class or something, when you have 1 equation and 1 unknown, then you can solve for that unknown. So for instance, if you had 2x plus 3 is equal to 5, right? And you could say that 2x is equal to 2, and then that would mean that x is equal to 1, right? So, and then if you have 2 equations and 2 unknowns, that's okay also. So when you have 2 unknowns, you need 2 equations, right? Because you need two equations in order to solve for any one of those variables. Then for 3 unknowns, you need 3 equations, and for 4 unknowns, you need 4 equations, 5 unknowns, you need 5 equations, and so on. You need the number of unknowns and the number of equations to be the same if you want to have a unique solution. So to make things a little easier, we're going to look at what each of these importance scores represents. So you remember we said before that they're really probabilities. And so each of these W, X, Y, and Z is each the probability that at any given time you're going to be on one of those nodes. And we said the higher that chance is, the more important the page is, and so on. Well, things about probabilities, first of all, is that they have to always be between 0 and 1. 0 meaning it'll never happen, 100%, or 1 meaning that it's certain to happen. So if you add up W, X, Y, and Z, that has to be equal to 1, because logically speaking, you have to be on one of the nodes at any given time. So they have to add to 1 because you're 100% certain that you will be on either W or X or Y or Z at any given time. And so we can make things easier by noting that these probabilities must sum to 1. And so we can say that W plus X plus Y plus Z must be equal to 1. So now you're probably wondering, well, now we have 5 equations, right? And that might be problematic because we only have 4 unknowns. Not saying that we couldn't do it, because as it turns out, you could still solve this using the 5 equations, as we will technically do, but we won't make use of each of the 5 equations when we do it. But basically, you only need 4 equations at any given time to relate these variables to one another. But this equation is much easier to use and easier to look at than, for instance, this equation right here. This equation is a little more complicated. We have a lot of divisions and things along those sorts. So this normalization equation is much easier to use. So we'll stick with that for now, and we will not use this equation. We could have also not used this one or this one or this one, but these are easier to look at because they don't relate all the variables at once. Right? This one only relates 2, this one relates 3, this one also relates 3, this one relates all 4 of them. So we'll use this equation with this equation, and this equation. Second is that we have to choose one of the importance scores as a reference. Or we don't have to, but it's just easier to do that, to choose one of them as a reference. And the one that we want to choose as a reference is going to be the one that we can then go ahead and plug into this equation. So then we can say, suppose we got everything in y, then we have some function of y, some function of y, and some function of y equals 1. Then we can plug that in and then solve for y, right? And then everything else would fall out of it. So let's first look at these equations, these 3 equations right here, and see which of the variables would be the easiest to work with as our reference. So let's choose z as our reference here, because we can pretty easily get everything in terms of z, right? We already have w in terms of z, then we can get x in terms of z, because we'll have w in terms of z, and then we can also get y in terms of z using this last equation. So that'll be probably the least tedious path. Now, again, you could choose any one of them, and it won't matter. It's just we're trying to make the math as simple as possible here, because we don't want to deal with heavy math. So we'll choose our reference value to be z. So to start off, then we'll go w x and then y and try to get them all in terms of z. So for w, we'll just use the first equation. We already know that w is equal to z over 3. So that's easy because then when we plug in here, we just have w equals z over 3. So we're done with that for now. Now let's move on to x. Now we want to get x in terms of z. So we have x equals w over 2 plus z over 3. So now, we already have w in terms of z, though. We know that w is equal to z over 3. So we can say that x is equal to w over 2 plus z over 3, which is equal to, then on this side, this w term over here, is z over 3 divided by 2, because this is just equal to z over 3, plus z over 3 again. So that's z over 6 plus z over 3. And then if we can, for instance, make each of them a common denominator, so we have z over 6 plus 2z over 6, which is then 3z over 6, which is equal to z over 2, 1/2 z. So now we have w is equal to z over 3, and x is equal to z over 2. So you can already tell now that since z is between 0 and 1, that x is going to have a higher importance score than w, because w is just 1/3 of z, whereas x is only 1/2 of z. Now we can move on to y. So rather than using, again, this equation where we'd have to plug in everything for w and then x, why don't we just work with this equation down here, because we already have, and we can say that y is equal to z minus x over 2. So we'll say y is equal to z minus x over 2, right? Because we already have y on this side, so we can just subtract x over 2 from both sides. And then we had x as before is z over 2. So this is z minus z over 2 over 2, which is z minus z over 4, which is just 3z over 4, 3/4 z. So now we have that y is equal to 3z over 4. So notice a few things. First of all is that we chose each of these three equations up here to get w, x, and y in terms of the reference variable z. And now we have those three relationships that we need in order to plug back into this equation. Then we can solve for z using one equation and one unknown, which is the basis for everything here. And also notice that we chose the simplest equation to work with first, right? Simply that w is equal to z over 3. We didn't have to do any substitution or anything in that equation. And then we moved on to the more complicated equations, and everything kind of fell out, and we used what we had before to solve for what we needed to do at the present. So that's the way to go about this, is that you sort of unlock different pieces of the puzzle, so to speak, as you go on, and then you use what you've unlocked in terms of what variables you've already gotten in terms of z to keep moving forward in the process. So moving along then, we can tabulate our equations again. Now we'll just tabulate the reference equations because those are much easier to work with. And z equals z, obviously. So plugging in, we can solve for z. So remember, we had w plus x plus y plus z equals 1. Now w is z over 3. So we have z over 3 plus x, which is z over 2, plus y, which is 3z over 4, plus z has to be equal to 1. So now we need to find a common denominator in order to be able to solve for z easily, or we could use a calculator too. It's either way is fine, but just to illustrate this here, the first common denominator we get would be 12, right? Because 4 goes into 12, 2 goes into 12, 3 also goes into 12, and obviously 1 goes into 12. So then we have to take 3 times 4 to be 12, so we have 4z over 12 over here, plus then 6z, because 6 times 2 is 12 over 12, plus, then we multiply this by 3, we get 9z over 12, plus 12z over 12. It has to be equal to 1. Right, so then adding this up, 4 plus 6 plus 9 plus 12 is 31. So we have 31z over 12 has to be equal to 1, which then means that z is equal to 12 over 31, which is equal to 0.387. It's easier to look at these in decimals because then we can more easily compare them. So now that we've solved for z, everything else will just fall out very easily because we already have w, x, and y in terms of z from our reference equations right up here. So we can backtrack for the rest. We get w is equal to z over 3, which is equal to 12 over 31 divided by 3, which is just 4 over 31, which is 0.129. We have x equals z over 2, which is 6 over 31, which is 0.258. And we have y equals 3z over 4, which is 9 over 31, which is 0.290. So now we can easily rank these. We see that z is the most important with 0.387, followed by y, then followed by x, and then followed by w.